Hello and welcome to this video on graphing functions involving cube roots. Alright, so in this video I'm going to be going over one example with several parts where we're looking at a function in which a cube root, right, that's a radical with an index of 3, right, in which a cube root is involved and the radicand, has some variable in it. And the first part I'll be asked to find the domain, of the function. What am I allowed to plug in for the input variable? Then I'll be asked to graph the function by plotting some points, right? So I'll make a little chart with some ordered pairs that would satisfy the equation. And then finally, using that graph, can make a statement about the range of the function, right? What's the set of the outputs, right? The y coordinates. Okay, so my example is a pretty simple one. I mean, they can get a little more complicated, but what I'm going to do for this example, you would do for even more complicated ones as well. So I have consider the function g of x, right? The name of the function is capital G. G of x equals the cube root of x, and then afterwards, notice this is not underneath the radical symbol, we have minus 1. Alright, so remember how what this means, right? The input variable is x, the output is called g of x, and then, over here is how you calculate the output. You take the cube root of the input and then subtract 1 afterwards. Alright, so in part A of this example, I'm asked to find the domain of the function. Right? So this is the set of all possible inputs, right? All the real numbers I can plug in for x, right, my input variable, and get a real number output. Well, I've talked about finding the domain of radicals in a previous video. We really have to pay attention to the index, right? This is an odd root, right? This has an odd index. And if you recall from, again, if you've been watching, if not, I'm going to state it again here. If a radical has an odd index, then the radicand, remember the radicand is just the expression inside the symbol, right? So that's just x here, a very simple radicand, just one term, x. If a radical has an odd index, then the radicand can be any real number. Right. So it wasn't like even indices, right? When you took a square root or a fourth root, the radicand has to be non-negative, right? Can't be negative. But with cube roots and fifth roots and seventh roots, odd roots, the radicand can be anything. Right, so that makes stating the domain a pretty simple affair here. X can be any real number. Alright, sorry about that. That marker is getting faint. Throw it away. So I'll state this: the domain of this function capital G equals, and first I'm going to write it in what's called set builder notation, and it's just it's the set of all values of x, right? My independent variable is x. It's the set of all values of x, just so long as, and then the condition afterwards, after a bar or a colon. Well, here x can be any real number, right? So the domain contains all values of x, as long as that value of x is a real number. All right. So this is just another way of saying that the domain is any real number. All right. Great. Or you can always write a set, that has infinitely many values in it, right? That's continuous in interval notation. Well, if you think about the number line, x can be any real number. I can plug in anything I want, negative a million, negative a billion, negative a trillion, going to the left forever on a number line. There is no lowest value in the domain then, right? There is no lowest domain value, lowest input. So to indicate that, I put the symbol, negative infinity, right, to indicate there's no lowest input. And then same thing, going from the far left end of the low end of the real number line to the high end. I can use any number I want up to 1,000, a million, a billion, a trillion. I get as large as I wish. There is no largest value in the domain, so I indicate that with the infinity symbol. Right? And you cap these off, right? You're writing an interval. And these are not numbers. I've mentioned this several times in other videos. Infinity and negative infinity are not numbers. They're concepts. They're ideas. So you couldn't like plug infinity in for x here. So it's not an input. So to indicate that these ends, negative infinity and positive infinity, are not in the set, we put parentheses on those. All right. So there we go. Here it is. It's very simple. I have an odd root, and you can plug anything you want, any real number, into an odd root, and you'll have a real number output. And notice also I don't see any denominators where I could possibly be dividing by 0, right? Remember, you can't do that. There aren't any parts of this where I'd have where I could have 0 raised to a negative power. You can't have that either, because that's essentially like dividing by 0. So we're good, right? The domain is all real numbers. I can plug in whatever I want. All right. Part B is, I'm going to take this function g, right, and graph the function using some point plotting. Okay, so I've got my axes all written out here, right? The horizontal axis will represent, possible values of the input, and the vertical axis, the y-axis here, I labeled it y, will represent possible values of the output, g of x. And so you could also call this vertical axis the g-axis if you want, because the outputs are, the value of g at x, g of x. All right, so as with other functions I've graphed in past videos, I'm going to make a little table off to the side here. Make a little chart where I'm going to, be plugging in values of x. I'll pop this up here. Plug in values for x. Now one column. In the next column, the outputs, capital G of x. And I'll even write how we're calculating it, right? Here's the rule. It's the cube root of x minus 1. And then in this last column, you don't need the last column really if you see the ordered pair, but I'm going to put the point that I'm plotting, right? The ordered pair with the x coordinate, the input, comma, and then the y coordinate, or the output g of x. And, ordered pair that I'll be plotting on my coordinate plane. And as with the square root, I did a video prior to this on graphing a square root function. Well, this is a cube root function, so I would like the radicand to be a perfect cube. That would make things real nice for me. Now, it doesn't have to be, right? I can plug in, we saw the domain was all real numbers, right? I can plug in anything I want for x. But I'm going to try plugging in things for x so that the radicand, the number underneath the symbol, is a perfect cube, right? So let's talk about what some perfect cubes are. Well, 0 is a perfect any power, right? 0 is a perfect cube. You can say that's 0 to the third, right? And then we can go, there are positive perfect cubes and there are negative perfect cubes, right? It's not like your even powers where they're always non-negative. So negative 1 is a perfect cube, right? That's negative 1 to the third power. Negative 8 is a perfect cube, right? That's negative 2 to the third power. So I want to plug these guys in. Right, -8, -1, and I could go, -27 is -3 cubed, and so on. And the positive perfect cubes, +1 is 1 cubed. All right, +8 is a perfect cube. That's 2 to the third, and so on. So I want to plug these in for the radicand. Now the radicand is x, so I'm going to have x be that, 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 right? So down my first column here, I'll plug in -8, right? So that when I plug it in, I have a perfect cube in my radical, right, in my cube root. I'll plug in -1 as well, and 0, and 1, and 8. And let's see what kind of points we get. Right, again, you can go to negative, plug in more. And I don't have to plug these in. I could plug in other values, right? I said already, the domain is all real numbers. So I could plug in, 3 if I wanted to. And I'll see what that gets me. Alright, so the first one, the output would be the value of g at -8, or, the cube root of -8 minus 1. Well, the cube root of -8 is -2, and -2 minus 1 is -3. So the point I'm going to be plotting as, input -8, output -3, right? So that's the ordered pair I'm going to plot on the coordinate plane when I move this page. The value of this function at -1 is, now I'm just going to say it this time instead of cluttering this up with a bunch of writing. The cube root of -1 is -1. Then -1 is -2. So I have, ordered pair, input -1, output -2. The value of g at 0 is the cube root of 0, which is, 0. Then -1 would be -1. So I have ordered pair, plot the point, 0, comma, and then output -1. Then g of 1 is, the cube root of 1, which is 1. -1 is 0. So I have input 1, comma, output 0. G of 8. You have the cube root of 8, which would be 2. -1 would be 1. So I have input 8, output 1. And again, just for fun, this isn't going to be really nice, but g of 3, that's the cube root of 3 and then -1. Now if you want to punch that into a calculator, right, the cube root of 3 is, definitely between 1 and 2, right, because 3 is between 1 and 8, right, 1 cubed and 2 cubed. So if that's between 1 and 2, and then I subtract 1, you'll be between 0 and 1. This number here is between 0 and 1. Right. So again, this isn't really nice. I know it's 0 point something. Just we'll see what points, where the points land when I start plotting them. Okay, and then the point I would plot, if I could actually eyeball it, input 3, output, cube root of 3 -1. Great. Alright, so I'm going to keep this table over here, and let's plot some points. Alright, so as I've mentioned, I've already got my x-axis and y-axis drawn, input axis, output axis. And I'm going to, I have this set up. I would like to be consistent here. I'm going to have every square on the horizontal axis represent 1 unit. And I'm also going to do that for the y-axis as well, the vertical axis, have every square represent 1 unit. Alright, so the first point on this is, -8 for the input, -3 for the output. So there's the origin. So that's -8. Alright, -8 for the input, -3 on the vertical axis, and -3 for the output. Alright, so we're talking, this location right here. All right, if you want to label the point as well, put the ordered pair next to it, that's fine, but that's -8, -3. Then I have -1, -2. So -1 input, -2 output. That's this location here. All right. Then I have 0 input, -1 output. So 0, -1. That's on one of the that's a y-intercept, right? It's on the y-axis. Got an x-coordinate of 0. Then I have 1, 0, an x-intercept. Right? 0, 0 coordinate for the y. So 1 for the x, 0 for the y. All right, and then 8, 1. So 1, 2, 3, 4, 5, 6, 7, 8. 8 for the input, 1 for the output. And that's this location right here. Now hopefully you see it's not a straight line, right? These points are not forming a straight line. They form more of a kind of a elongated S-curve. Right, so, and if you wanted to see other points, now this, again, this last one, you can eyeball it if you want. Got input 3, so 3 on the x-axis. And the output is the square root of 3 minus the cube root of 3 minus 1, and as I mentioned, that's going to be between 0 and 1. So when I go to input 3, the output's going to be between here and here. All right, so I'm just going to keep that in mind. Let's say it's about here, right? This little dot, and you could go to other points. Now, again, it would be easier to just plug in perfect cubes. Like I could go out to 27. And then have an output of 2, right? So 27, 2, 64, 3. Going this way, -27, -4, -64, -5. Like, so the further out right you go, the higher you'll get, and you'll get higher and higher and higher forever, right? If you go out to 1,000, you'd be at an output of 990. Sorry, not you have to. You go up to 1,000, right? The cube root of 1,000 is 10, minus 1 would be 9. So you'd have to go out to 1,000 to get up to 9. But you can go out forever, right? I can go up to 1,000,000 to get really high, and 1,000,000,000, or 1,000,000,000,000, whatever, right? So it's going up forever that way, and same thing, it's going down forever as you move to the left. Like I said, if I go to -1,000, cube root would be -10, and then minus 1, you'd be down at -11 for the output. And again, the further out left you go, the lower the output. So I'm getting this like elongated S-curve thing here, where it's getting higher and higher. And that's kind of crappy there. Sorry. Put a little arrow. That is getting higher and higher and higher as I move right, but very, very slowly. Same thing this way. Right? It's getting lower and lower and lower as I move to the left, all right, but just very slowly, all right, and I'll put the letter G next to this so we know it's the graph of this function G. Excuse me. Great. All right. Okay. So again, a lot of very similar to plotting any function, right? Input in values for your input variable. Make sure they are actually values from the domain. Which was all real numbers here, so great, anything you want. And then, once you have the outputs, you'll have an input and output pair that you can plot a point for. And once you have enough points, hopefully you get enough points down to where you're seeing a pattern. Like I was seeing this elongated S shape here, and then you can plot the rest of the graph. All right, and look at that point at 3. All right, remember I said you have the point 3 cube root of 3 minus 1. That's this point right here on the graph I just drew, and you see how, I'll label it, that'd be 3 comma cube root of 3 minus 1. See how that point has a y coordinate between 0 and 1 like I said it would? So again, you can plot points that don't have, integer x values and y values. It's just harder to do because again, they're not nice. Right? It's harder to eyeball those. Great. All right, so now that I have that, I have the domain. Domain is all real numbers. got the graph, and then based on this graph, right, part C is based on the graph. All right, part C, based on the graph, determine the range. Remember, the range is the set of outputs, right? The set of the y coordinates. So I'm looking at the vertical axis this time. Bottom to top, always low numbers to high numbers. If you're looking at the x-axis, you look from left to right. Look from the bottom to top. And you see that -1 is in the range, right? The y-coordinate of -1 is used for this point. 0 is used at that point as a y-coordinate. 1 is used at that point as a y-coordinate. -1 is used, -2 is used, -3 is used. The cube root of 3 minus 1 is in the range, right? It's a y-coordinate. And can you see that because this is going down this way forever, and this, as you go to the right, it's going up forever, every single y value, every number on the y-axis is going to be used as a y-coordinate in some point on this graph. So not only is the domain all real numbers, but the range is the entire number line. Remember, the axes are just number lines, right? The range is also the entire real number line. All right, so the range of G equals, and again I'll write it in a couple ways with the set builder notation, the curly braces, and we're talking the range this time, so we're talking values of y coordinates. So the range of G is every value of y as long as y is a real number. All right, so this is again another way of saying that the range is all real numbers. All right, you pick up, how about 10? When y is 10, there is some point, it'll be way out here, you have to go, keep going up and up and up and up and up. But there is a point with a y coordinate of 10. There's a point with a y coordinate of 1,000. There's a point with a y coordinate of -7, and so on. Pick any number on the y-axis. There is a point on this green graph, on the graph of G, that has that number as a y coordinate. All right, or like with the domain here, the range of G, I can state it this way, or in interval notation. Remember, the interval for all real numbers was the interval of numbers from -infinity to infinity, right? That's representing everything, every possible real number. And again, parentheses on those ends, because infinity and negative infinity are not numbers. So they don't actually belong to the set. Great. All right, so there you go. Domain's all real numbers because it's an odd root. I don't have to take the I don't have to worry about, do I have a negative radicand or a non-negative radicand? The radicand can be anything with an odd root. Making a graph, make a little chart, plug in inputs, get outputs, and if it's a square root, plug in values that'll give you perfect squares as a radicand. If it's a cube root like this one, plug in values so that you have a perfect cube as a radicand, right? That'll just make finding outputs and plotting points that much easier. And then finally the range, right? The range was all real numbers as well. Again, you're looking for what outputs are used, right? When you're talking about the range, what's the set of the y coordinates that are used in this function? Wonderful. As I like to say at the end of these videos, do the best you can to try to learn the material on your own before you go looking for help. Because I find that people who take the time and the effort to learn something on their own tend to remember it better and remember it for longer and are more proud of it. So of course, read the material, read through the author's examples, perhaps even try to work on the solutions to an author's example before you see how the author did it, and then compare your work with the author's and see if you can learn from some mistakes there. And of course, do plenty of exercises, practice problems, check answers, if they're made available, so you can check yourself, see how you're doing. And don't give up on a problem or an exercise after just 1 or 2 attempts. Very often in mathematics, there are several approaches that'll work for any particular problem. So if after several attempts, you're still not seeing how to do something, still not getting it, maybe you should read through the material again. Maybe even a third time, more slowly, more deliberately. Take good notes. Because if you've been doing some problems, there's a good chance you have a better idea as to what the author wants from you, what the author is asking you for. So then you know better what to look for when you read through the material again, or that third time. And maybe you'll see some things will pop out at you that didn't the first time, and make it that much easier to work on the problems. But if after that, if after several read-throughs of the material and several attempts at the problems, you're still not getting it, still not making sense, it's not a sign of weakness whatsoever to go out asking for help, go looking for help. That is what other people are there for, to help you. So ask a teacher, a tutor, a friend, someone in your class who you know knows the material well and is willing to help. Look for supplemental materials online. There's loads of it out there. Look for videos online. There's tons of those too. Videos like this one, or plenty of other ones out there better than this one. I assure you they're easy to find. But just, keep at it. Keep practicing. Stay persistent. Don't give up. And above all, I think this is the hardest part, but probably the most important, is to believe in yourself and stay positive about the subject. Try to have fun with it. Make it a game. You learn through your failures. So don't be too discouraged. Believe that you're going to make it through. Believe in your abilities. When you struggle, when you fail, those are the times when you can learn the most. Learning from your mistakes. So keep at it. Keep practicing. Stay persistent. Stay positive. Don't give up. And I just know you'll get it eventually. Thank you very much for watching.